Welcome to this lecture series in real analysis. In this lecture, we look at the notion of sequences, and all we need to know is what are real numbers. And we have discussed this at length, so let me not get into the details of this and get started. So here are some problems for practice. And now we begin. So first we will discuss what are absolute values. This is something that we know from high school, but no harm in revising. So we define a function, which we denote this way, which consumes a real number and outputs a non-negative real. So this notation is all those real numbers which are non-negative. Okay? So this function has all the reals as its domain and all the non-negative reals as its target. And what does it do? It picks x and outputs x if x is non-negative and minus x if x is negative, right? And its output is written as this, and we read it as the absolute value of x or the mod of x. All right. So in notation, this is x going to that thing, and this is called the absolute value of x. Okay. You can think of it as measuring the size of x. All right, so enough about that. And here is one way to visualize it. This is the graph. This curve is the graph of the absolute value function. At 1, it takes the value 1. At minus 1 also, it takes the value 1. And it grows linearly towards, linearly in this half and linearly in that half. But there's a kink here. So I'm sure you have seen this graph before. All right, and one comment, this difference, or rather the absolute value of the difference of two real numbers can be thought of as the distance between x and y, right? So if we have, let's say the real line is denoted like this. Somewhere we have origin just for reference. Here we have x, here we have y. So the absolute value of the difference of x and y is kind of this length. This is how we can think about it. Okay. Okay, great. And lastly, we need to recall the triangle inequality. It's a very simple thing. It says that if we have two real numbers, or rather three real numbers, just two real numbers, then this happens. There's a reason why this is called the triangle inequality, but let us not get into that. This is what it says, and you can prove it as an exercise. All right, so this is just a quick recollection of the absolute value function. And now we need to define one more concept. So we say that a subset A of R, and when we say a subset, I mean a non-empty subset. So a non-empty subset A of R is said to be bounded if there is some real number k, there is some positive real number k, such that this happens, right? So we say A is bounded if there is some positive integer k for which this condition holds, meaning the size of each element of A is controlled by the number k. In pictures, if this is the real line, then all we are saying is that there is some k such that the entire set A is between minus k and k. And since we have put a less than equal to sign, the set A is allowed to have the end points here. So basically, if there is some finite interval which contains the set A, we say that the set A is bounded. It's a very, very simple definition. Okay, and just for example, maybe you can, well, I don't have a very good example, just the obvious ones. Just take any finite set. So any finite subset of R is bounded. That should be clear. And you can take any interval, so any interval of the form, let's say it's an open interval, a comma b, where a and b are of course real numbers, is bounded. And you can construct infinitely many examples. Alright, so now we start with the main concept of this lecture. What is a sequence? So fix a non-empty set X, then first we will informally define what is a sequence. A sequence in X is, informally speaking, such a thing is a list x1, x2, x3, ... where each xi is an X. So a sequence is an infinite list where each element in the list is in the set X. That's what a sequence is. And there is no compulsion or demand that these be distinct. This could be just the same element repeated infinitely many times. That is also a sequence. Okay, so X, 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 X is a sequence. Now, why is it informal? What is so informal about it? Well, in standard mathematics, in the way mathematics is usually written, we define concepts on the basis of sets and functions and relations and operations formed out of them. There is no set way of, taking a sequence, an infinite list or any such thing. So we need to formalize this, and this formalism actually helps. So formally speaking, a sequence in X is a function from the naturals, let me not give it a name, from the naturals to X. That is the proper definition of a sequence. What does it do? It picks a natural and outputs an element in the set X. And let us correlate this definition with what we just learned. So if we are given such a thing, we can create such a thing. What do? Let's say this is F. So then what you can do is just list out the images of F in sequence, meaning F1, F2, F3, just create this infinite list, and that looks like this thing. And if we are given such a thing, we can create a function from the naturals to X. So the relationship between the informal way of writing things and the formal definition should be very, very clear. All right. So yeah, maybe I will write it. So if F is a function, meaning a sequence in the formal sense, then defining xn equals fn for each n allows us to write this thing, and this is the more natural way of thinking about a sequence. So this informal thing is how we think of a sequence. The formal picture may sometimes be invoked to facilitate a few arguments. So one should be able to move back and forth between these two things. And with the time, in fact, most of the time we do not resort to this formalism. We just express things like this. And once you have defined things properly, this does become formal now. Once you know that what this means is that This is now as formal as that. This becomes now a notation to mean this. Okay, so I hope this was clear. And just for an example, as we already said, it's a very, very basic example, not very illuminating. So let x be some element in the set x. We may define this function which takes n to x for all n. This is also a sequence. So this is an example of a sequence which may be written this way. Okay. Another important notation which is very, very useful and rampant. So here is a point of notation. Given a sequence, let's say it's written in this way, we may alternatively write this. Either that, or one may write this. Okay. So instead of writing this out in this fashion, we write the generic term and put parentheses around it, and then indicate the dummy index. So these are two notations. And another notation that is used when the context is clear is just this. So this is a little bit of an abuse. Of course, this has to be understood that n is a dummy index. But when it is clear from context, we just write that, or not many times. This is much more convenient. So one should be aware of these notations. Okay. So now we will be discussing real sequence. This is basically what is of interest in this lecture series, a real sequence. We will not be interested in sequences valued in arbitrary sets. So what is a real sequence? You can guess. A real sequence is a sequence in R. Right? So that's the definition, which means that you may think of it as a function from the naturals to R, or you may think of as an infinite list of real numbers. Okay. Yeah. And yeah, one more thing I want to say is that sometimes what we do is we start a sequence from 0. This thing can also be called a sequence in X. So here you're just changing the indexing set. Let us not waste time on such small things. So yeah, so we have the definition of a real sequence, and now let us look at examples. The first example is define xn as -1 to the power n for all n. This is of course a sequence. In the formal way, you can say it's this function. All right, but it helps to look at the graph of such things. And here on the x-axis, even though we have drawn the entire line, the domain of the function is only naturals. So these are the only points on which f takes some value. So this is the graph of f. And what does it do? At 1, it takes the value -1. At 2, it takes the value 1. At 3, it takes the value -1, and so on. So these dots are all that there is in the graph, but we have joined them using dotted lines just for visual convenience. So it's a very simple thing. And the other example is xn is equal to 1 by n for all n. Okay. And in the formal sense, in the formal way, one can write that thing. And again, one can draw a graph. So here at 1, you get the value 1. At 2, you get half. 3, you get 1 by 3. So it kind of decreases and dies down, so to say. All right, so these are two simple examples, but what one can do is once you have two sequences, you can create more out of them. So suppose we have two sequences, and this time we will use this notation. So these be two real sequences. Then we may define two sequences, an and pn, as an is the addition of xn and yn, and pn is the product of xn and yn. So this is for all n. Right? So this is called the sum of these two sequences, and this is called the product of the two sequences. In the formal picture, if we call this f, and similarly the other one is g, meaning that one is g, then what is this guy? That is just the pointwise addition of the function f and g, and that may be written this way. And this guy is just the pointwise multiplication of f and g, and that may be written that way. So that is just a change of notation. All right, and you can similarly create other such examples, but these are two basic ones. All right. So now we will discuss bounded sequences. A real sequence is said to be bounded if the corresponding set. So a real sequence, let us give it a name or have a reference to discuss it. So a real sequence, let us use this as the notation for the real sequence. Then we say it is bounded if this set is bounded. Right? So it's a very, very simple definition. This is not the sequence itself. This is the set of all the elements that feature in the sequence. If, for instance, the sequence only repeated a single thing over and over, for instance, this kind of thing, this is a sequence, while in that case, this thing would become just the singleton x. Right? So this is not the same as that, because this just completely forgets about the ordering in which elements appear. I mean, that is one of the reasons. Here you have kind of a data which gives you a real number for every natural number. That's not what you're getting in this set. If I give you this set, this could be just some finitely many things, for instance. You wouldn't be able to reconstruct this guy. So this is just a very coarse derivative. By derivative, I don't mean differentiation or anything. By derivative, I mean just something that is derived out of something that is given. So this is just something very coarse that arises out of this. Okay, so we say this guy is bounded if the corresponding set is bounded. In other words, you can think of it in this way. I mean, this is a geometric picture, so this is one way to express it geometrically. If this is the real line, we say this sequence is bounded if there is some k such that each xn is within this interval minus k comma k. That is one way to state it, but the other graphical way to state it is the following. Suppose we draw the graph of our sequence like we did in the previous two examples. So on the x-axis, we will have all the natural numbers. And for each natural number, we will plot the corresponding element of the sequence. So here I will plot x1, then x2, x3, and so on. Boundedness is merely saying that there is some band around the origin. So there is some band of width k. There is some band of width k where the graph will be sandwiched, between which the graph will be sandwiched. You will not find the graph violating this boundary at any point. So that's what a bounded sequence is. Okay, too much time spent on a very basic thing. So suppose now we have two sequences, two bounded sequences, and this time we have used the lazy notation to express a sequence. I should be writing this, but I dropped that subscript because it is kind of clear from the context what I mean. So we have two bounded sequences, and we are saying that the sum sequence and the product sequence, which we discussed, are also bounded. So for the sum sequence, let me just give a quick argument for the sum sequence, and the product sequence will be an exercise. So since xn is bounded, let me write it in one line. So since xn and yn are bounded sequences, there exist k and l such that for all n. So yeah, so I mean, maybe I could have written this here itself. So in other words, let me emphasize this. So in other words, a real sequence xn is bounded if and only if there is some real number k such that the absolute value of xn is bounded by k for all n. So I'm just recasting what was written here, or rather just unraveling the definition of boundedness of a given set. That's all that I'm doing. So maybe it's all hodgepodge. Let me make some space, which I don't know how to do. Yeah, hopefully this is clear enough. All right, so that's all we did. We had a bounded sequence xn and we had a bounded sequence yn. So there is some capital K for which this happens for all n, and there is some capital L for which this happens for all n. And now by triangle inequality, we have this, which is of course less than equal to that for all n. And therefore, the summed sequence, meaning that guy, that is also bounded. So just an immediate application of the triangle inequality gives us boundedness. However, all of both of these facts, the fact that the sum and the product sequence are bounded, is just a very intuitively clear fact. So all this verbose thing should not confuse you. This is just a formal proof writing exercise. The mathematical content is not at all elusive. Okay. Finally, we want to discuss what is a subsequence. So fix a set x, and of course it's a non-empty set, and fix a sequence in x. Okay, so we say that a sequence yk, k going from 1 to infinity. So here the dummy variable is not n, we are using k for the dummy variable. So this is a subsequence of the given sequence if there exist natural numbers n1, n2, n3. So these are natural numbers, I should mention that, such that yk is x sub nk. Alright, so pause for a moment to think about this definition, and now let me illustrate what we are trying to say. So we have this infinite list, x1, x2, x3. Let me make some more. We have this infinite list. What is a subsequence? You pick a natural number 1 and select some guy from this. Okay, let's say we choose this. Then you have a natural number 2, and then you select some guy that comes after. You select that. Then 3, you select some guy that comes yet after that. So this way you will be selecting out kind of a, I don't know how to say it. except to say that a subsequence of the given sequence, right? You are throwing away some of them, but selecting the others, and you are maintaining the order. So that is what is a subsequence. Here it is important to make, I should have given the subscript here, because otherwise one may get confused. Typically one doesn't get confused, but one can get confused. So here the subscripts are important. All right. So this better be an increasing sequence. That is very important. So a very simple example of a subsequence would be the sequence itself. So if this is a sequence, then you define yk is equal to xk. That is a subsequence of that. Basically, we have repeated the same sequence again, and that is still a subsequence, of course. Okay. We should take examples. So one example is the following. You can define, so your sequence xn is, let's say, for all n, and you can define your yk as minus 1 to the power k square, right, for all k. Then yk is nothing but x sub k square, and hence yk is a subsequence. Of course, when you substitute 1, 2, and 3 in place of k, this is an increasing sequence of natural numbers, and hence yk is a subsequence. So what you're doing is you're rejecting, the elements of the sequence which correspond to non-perfect squares. Just some arbitrary selection. So that's a subsequence. Let us look at the formal version of this definition. How do we express the same definition in a more functional form, basically? So if f is a sequence in a set X, then a subsequence of f is any sequence in X obtained as follows. So what you do is you pick a function phi. Maybe I will make a diagram that is better. So we have this sequence f. What you do is you pick a function phi which is strictly increasing. So phi is strictly increasing. What that means is phi 1 is less than phi 2 is less than phi 3, and so on. So you pick any such function phi and then you compose it with f. This is a subsequence. Any such thing is a subsequence. So what does phi do? Phi is telling you which ones to keep. You are given a sequence. The phi is basically, phi 1 is basically n sub 1, phi 2 is n sub 2, phi 3 is n sub 3 basically. And those are the ones that you keep. Everything else you throw away. So this one is precisely in this above notation, it becomes yk or x sub nk, where you're writing nk to mean phi of k and xn to mean f of n. Okay, so I hope you can make connections between this picture and that picture. I have said it in words and you should mull over it. With that, I want to end this lecture. As usual, like, comment, share, subscribe, and I will see you next time.